Welcome to The Explainer. Today we're going to do something a little different. We're not just going to talk about AI, we're going to build a digital brain, an artificial neural network from the ground up. So let's just dive right in.
All right, so where do we even begin? Well, the best place to start is with the thing that inspired it all, our very own brain. The whole idea of an artificial neural network, an ANN, it's really just a simplified, coded-up version of the biological network that's firing away inside our heads as we speak.
So check this out. On one side, you've got the real deal, that complex, squishy, organic cell that learns from, life experience. And on the other side, its digital cousin. It's a much simpler model that learns from raw data. And that switch, right there, from experience to data, that is the key idea we're going to unpack today.
Now, this table is really interesting because it shows a huge trade-off. Just look at that computing row. Our brains, they are absolute masters of parallel processing. Everything is happening all at once, a beautiful chaos. But ANNs, they're usually sequential. They work step by step. And honestly, that one single difference, it explains so much about why they're so powerful, but also where their weaknesses lie.
Okay, so we've got the big picture. Now let's zoom way in, down to the single most important building block of our digital brain, the artificial neuron. You might also hear it called a perceptron. Just think of it as the basic computational Lego brick of the whole network.
First things first, let's talk about weights. The best way to think about these is like tuning knobs. Yeah, tuning knobs for every single input. A high weight means that input gets a bigger say in the final decision. A low weight, it gets less of a say. And really, the whole game of learning for an AI is just about finding the absolute perfect setting for all these little knobs.
Okay, next up is the bias. This is a fun one. It's kind of like an extra little nudge for the neuron. It's a baseline activation level. It gives the whole network more flexibility. So a neuron can still decide to fire, to activate, even if all its main inputs are kind of quiet. And last but not least, we have the activation function. This is the big boss, the decision maker of the neuron. It takes the grand total of all the weighted inputs and then decides, okay, what's our final output going to be? And here's the crucial part. It adds something called nonlinearity. That's a fancy word, but it just means the network can learn really complex, twisty patterns, not just boring old straight lines. So to put it all together, every single neuron does this little two-step dance. Step 1, it gathers up all the incoming data, multiplies each bit by its special weight, adds them all together, and throws in the bias for good measure. Step 2, it pushes that final number through the activation function to get its output. That's it. Seriously. That's the core operation of a digital neuron happening over and over again.
But a single neuron on its own isn't all that powerful. It's just one little building block. The real magic, the real power, happens when we connect thousands or even millions of them together. So how do we do that? How do we go from a single neuron to a full-blown network? Well, we organize them into layers.
So, a standard network usually has three kinds of layers. First up, you've got the input layer. Think of this as the front door. It's where all the raw data we want to look at comes in. Then, in the middle, you have the hidden layers. There can be one or there can be many. This is where the real work gets done, all the heavy computational lifting. And finally, you have the output layer, which spits out the network's final answer.
Okay, that's a lot of theory. To make this way more concrete, let's follow the data on a journey through the network using a classic real-world problem. Let's imagine our new digital brain's job is to look at an email and answer one simple question. Is this spam?
Right, so the first thing we have to do is turn that email into numbers the network can understand. So our input layer gets the simple little list, a feature vector. We're just checking for keywords. Does the email say free? Yep, so that's a 1. Does it say win? Nope, so that's a 0. How about offer? Yep, another 1. So our input data is just that list of numbers, 1, 0, 1.
Okay, so that input vector, 1, 0, 1, now hits the hidden layer. And here's where we see the magic of weights. Each neuron, H1 and H2, takes that exact same input, but, and this is key, it multiplies those numbers by its own unique set of weights. So, as you can see, H1 crunches the numbers and gets 0.8, while H2 gets negative 0.1. The network is already starting to create its own internal, abstract idea of what this email is about.
Now, those new numbers from the hidden layer, that 0.8 and that negative 0.1, they become the input for the final output layer.
It does one last round of calculations, runs the result through its activation function, and out comes a single number, a final probability. The network's verdict? 0.636. So what on earth does 0.636 mean? Well, that's the network's confidence score. It's the probability that this email is spam. And since that number is bigger than our cutoff point, we'll just say 0.5, the network makes its call, spam. And boom, just like that, the data has flowed all the way from the input to the output, and we have a decision.
Okay, but wait a second. That leaves one giant question hanging in the air, right? In our example, all those weights, they were just sort of there. We just had them. But how did the network know which numbers to use for the weights? Well, that is where the real spark of intelligence comes in. It's a process called training, and the engine that drives it is an amazing algorithm called backpropagation.
So think about it. If you want to learn from a mistake, first you have to know you even made one and how bad it was. That's exactly what the loss function does. It looks at the network's guess, compares it to the actual right answer, and then calculates an error score. It basically just tells the network, hey, you were this wrong. So learning is really just a loop, a cycle that goes around and around. First, the network makes a guess. That's the forward pass we just walked through. Second, it uses that loss function to see how badly it messed up. Third, and this is the cool part, it works backwards through the network to figure out how much each and every weight contributed to that mistake. And finally, step 4, it nudges all those weights, just a tiny bit, to try and do better on the next attempt. And it does this over and over and over, thousands, even millions of times.
I know. That quote sounds super complicated. But here's the simple idea behind it. Backpropagation is basically just a really clever use of calculus. It calculates something called the gradient for every single weight in the entire network. All you need to know is that this gradient just points in the direction of less wrong. It tells the network exactly which way to nudge each of those millions of tuning knobs to get the total error score as low as possible. It's a systematic way to learn from mistakes on a massive scale. All right, so we've built our neuron, we've stacked them into a network, and we've even figured out how it learns. Let's take one last step back now and look at the big picture. Because we need to talk about what makes these things so incredibly powerful and also kind of strange.
So here's the deal. The number one strength of these networks is their uncanny ability to find super complex, nonlinear patterns in huge mountains of data. I mean, patterns a human being would just never ever see. But that power comes with a paradox. Because the thinking is spread out across millions of tiny little weight adjustments, it can be almost impossible to point to one spot and say why it made a certain choice. And that's why you always hear them called black boxes.
So why should you care about any of this? Because this simple little architecture we just walked through, neurons, layers, and this learning process, this is the engine driving some of the most world-changing technology we have right now. We're talking about everything from the instant language translation on your phone to the complex vision systems that let a self-driving car see the road. The core ideas are exactly what we just covered.
And that really leaves us with a huge, fundamental challenge. We're building these digital brains that are getting more and more powerful at a mind-boggling speed. But are we also by accident making them harder and harder to understand? Maybe the biggest question in AI right now isn't just how can we make them smarter, but how can we make sure we never lose the ability to ask them why? Thanks for joining The Explainer.